So yeah, we are discussing this error rate, and then now we discuss about this base error rate, and the definition of it is as follows. Okay, so suppose we first determine y, and then given that we generate x, and then we consider the example of y being male or female, and then we are considering the height of a person, right? And then yeah, given this generation process, we first p of x comma y is determined as p of y first, right? And then x given y, right? Okay, so in this case, x is determined only after y is determined. So for example, so we can assume that this p of x given y as a particular value is actually existing and determined. 예, 나옵니다. 그거 주시면 제가 건전지 갈 수 있을까요?
저거 케이블 쓰시는 게 놔주시면 돼요.
이거요?
네.
아, 이거 저기 어떻게 이거 저기 제 다음에 오면 이걸 또 저기 갖고 오긴 했는데 이게 좀 호환이 안 되나 본데.
그러시면
네. 여기 비치를 할 수는 없나요 지금?
비치는 안 되고 바다
어디서 받는지 좀 알려주시고요.
225 여기 위에 바로 있지.
225에 누구 찾아가요?
저 찾아가시면 바로.
뭐 케이블도 들고 다니고 보따리 장사도 아니고. 네. Right. So yeah, let's think of this p of x, which is a height distribution, when given y as maybe 1 or 0 to make it consistent with the previous notation. Okay, so in this case we can consider the distribution of a height, which is an average of maybe 170, and then some distribution which looks like Gaussian, and then we can also think of the height distribution when given y is given as 0 or female, which is another distribution of this guy. Okay. Okay, so in this case, let's imagine this p of y given x. Okay, so this is our posterior distribution, which reverses the generation order of this generation process. Okay, so what will be the distribution of this guy when, for example, given x is x is given as 168, for example. Okay, so in this case 168 is around here, right? And then in this case we can see that the distribution or the probability of observing this 168 when the label is given as male is about this much, right? And then also when this person is given as a female, and then the probability will be something like this, right? So intuitively in this case, when fixing our input value x or this observation as a particular value, and then bringing those values from these two conditional distribution, okay, and then we can easily determine, or the reasonable kind of policy to perform the classification is to pick up or choose which probability is higher between the two. right? And so in this case, it is reasonable to choose this higher probability that corresponds to this green line, which comes from this probability distribution when the label is given as 1, right? Okay, so in this case, when fixing x as our input feature, and then we just compute this, and is also 168, right? So we consider all the possible cases that considers the same variable 168 comes from this class and that class and so on, right? And then we just consider or just compare between them, okay? And then we just choose argmax p x is equal to 168 centimeter and p of y given x is equal to 168 centimeter, and here we choose the y. Okay, so here one thing that we didn't consider here is actually the prior distribution of y. So in this case, so these two values are actually this guy, p of x is 168 given y is equal to 0, and this value is p of x is equal to 168 where y is given as 1, right? So in this case, comparing these two, actually we are not just looking at this value, but we are looking at p of x given y and still y. Okay, so picking up one between the two will just correspond to picking up this guy where y is set as 1 or y is set as 0 and so on, right? But here we considered actually this guy, p of y given x is equal to 168, right? So this is clearly different from that one. And then how can we relate them? So this is where our Bayes rule comes into play, right? So in this case, so we actually want to utilize this probability distribution, which is posterior distribution, when x is fixed as a particular value, and then what is the distribution of our y, okay? So it is clearly the class of a Bernoulli distribution, because what is the possible y values? It is either 0 or 1, and then between these two possible outcomes, it will have a particular probability, right? And so it can be viewed as Bernoulli distribution where the probability of this guy being 1, if that is 0.7, and then the other one is 0.3, right? Okay, so in this case, we just reformulate or rewrite it into this form, p of so we can write it into this form, joint divided by this x of y. Then it is represented as, so this joint is represented as y and times p of x given y divided by p of x, right? Okay, and then here we can further rewrite this p of x, okay? So we can yeah, let's think of this P of x. So P of x, what is the meaning of P of x? So it is like P of x being equal to 168, right? So what is the overall probability of observing the person having the height of 168 regardless of their gender, right? So in this case, we can actually represent this process or this probability in terms, yeah, by following this generation process. So in this case, x will be generated only after y is determined as a particular value, right? So x is not directly generated, but it's only generated via or through a particular y value. So in this case, in order to arrive at this value, we can kind of consider all the possible intermediate cases by just changing or by considering each possible value of y that will be needed, that is necessary to generate our value x. So in this case, it can be represented in this form. So y being 0, plus P of y being 1 and P of x is equal to 168, like this one, okay? So intuitively, yeah, we can think of it as, yeah, considering all the possible routes by just changing different y values and then forming this probability and then summing all of them up, okay? So that will be the marginal probability value corresponding to this x being 168. But also it can be, yeah, formally written as this form. Let's first consider this joint, okay? This joint, and we consider this joint probability when given, when x is given as 168, and then we we just sum this joint probability over all the possible x values, okay? So in this case, we know that, I'm running out of this blank page, but we know that P of xy, and if we sum them up over all the possible y, and then we obtain this marginal distribution over x. Okay, then yeah, and then up to this point, x is our unknown, and also y is unknown, right? But we consider all the possible y's, which means that we just plug in every possible value of y in this process, okay? And then what is the probability of seeing one? And then given that, what is the probability, of this observing x as 168 and so on, right? And then what is the possible, so I'm just rewriting it, and then we just add them up, and then it is this guy, and then this is actually defined as our marginal distribution, right? And then let's okay, so let me just give an intuition to give you deeper or easier understanding of this marginalization, which obtains the marginal distribution out of joint distribution. So suppose this is our joint distribution, where for each combination of x and y value, what is the density value? Okay, so just like the previous case, what is the probability of jointly observing the person that is a male and having the height of 168? What is the probability, overall probability of seeing that particular combination? Okay, so we can think of this joint density in this form, and of course, because this, if it is the density function, and then all the integrals or all the volume under this mountain, okay, all the volume should be equal to 1, because that is the requirement or condition to be the probability distribution, right? And then here, the condition, let's think of the conditional distribution intuitively from this one. So, okay, so let's think of this as x and this as y. Okay, and then what is the? Let's see. Let me just bring that in. Okay, so suppose this is an x and this is y, and suppose this is our overall joint density, and then let's consider this conditional density. Okay, and this conditional density assumes that this is given as a particular value. And so suppose this is 10, for example. Okay, and then in this case, the intuitive understanding is, so along x being 10, okay, and then we just slice this function along this, okay, along this direction, okay, and then we will obtain some curvature like this kind of curvature, okay. So that is our conditional distribution of P of y when given x is fixed as 10. Okay, and then so this is not it. So we need additional normalization. So so this conditional distribution is formally defined as follows. So x comma y divided by P of x, right? So what is P of x? So P of x is in general, this P of x is not given as a simple value, or this is not given as an independent and specific value, but it is just computed. This is just computed value of just performing this integral over all the possible y value. Okay, so what does that mean? So for example, x is 10, so x is 10. What is the probability of P of x, which is a marginal distribution, or the integral of joint over all the possible y? So okay. So think of this slice, okay, this sectional kind of shape, and then let's bring that into over here. So it is too curvy, but something like this. Okay, so the area under this curve can vary, right? So in this case, it seems to be the area seems to be a little bit lower than the other part. For example, around this middle, and their sectional narrow shape or mountain may have much higher or larger area than this one, right? But we assume that this x is given as a fixed and particular value, right? So whether this x has the overall kind of small probability or large probability of this conditional distribution or this conditional kind of probability of y given a particular x value. So we already assume that x already happened. So we kind of we normalize this kind of area to sum up to 1. Okay, so yeah, bring this into the sectional image. And what is this axis? Of course, this axis is y, right? And overall, when x is given as or fixed as 10, and then this probability or this area is not that high. Okay, so this area is only like 0.3. Okay, and then yeah, this is a 0.3, and this guy, the integral, is actually corresponding to this area. Okay, so we divide it by this area, and then we just yeah, if we divide it by 0.3, and then we just boost this line vertically, so that their area or their sum under this curve is equal to 1. Okay? So it's like the same shape, or something like this. Okay. So this is a intuitive understanding of this conditional distribution. And then what about the marginal distribution? So for example, so this is the marginal distribution, but we only considered, so this is the definition of the marginal distribution, but we only considered it when x is fixed as 10 in this particular example, right? Okay, so in this case, what if we consider all the possible x's? Okay, all the possible x's, and then consider this p of x itself. Okay, so in this case, you can think of it as, so what is this probability, which is x, p of x, right? So this is when p of x given as 10 is 0.3, right? So what if we change x as 9? In that case, we start from here, right? So we also obtain the sectional kind of shape of this mountain, and then obtain the area of it. And suppose that this area was 0.18, and then if we change x with the 20 or 30 and so on, then we can obtain this area values along this sectional kind of curve or shape, right? Okay, and then yeah, those values, and then mapping it along this x direction, and then when it is 10, and then it is 0.3, and then 9 and 0.18, and so on. And then we can obtain their own kind of curve along the x. So this is a marginal distribution, right? So it's like, so you you filled up all these sands or particles under this mountain as kind of particles of sand. Okay. So in this case, we just squeeze them along this x-axis, and then if it is squeezed much more, and then this vertical bar will be elevated or gets higher and higher, and along this direction there is not much sense, and then even when accumulating them onto this x-axis, it may not be that much high, right? But at least this kind of accumulating these these sands along this y-axis, so that we consider all the possible y's, and then remove y as a variable. So we no longer have y as a variable, we only have the variable 1x, right? So this is the definition of this marginal distribution, right? So this is the definition or kind of intuitive kind of understanding of p of x, and similarly p of y is also cumulative version along the all the possible x-axis. Squeeze them and then just stack them up vertically, and then obtaining the resulting curve, and that will be P of y. Okay. And again, what is the conditional probability? We slice it, okay, at a particular value given as a conditional value, and then we consider this curve. Rather than consider all the other curve shapes, right? And then we only consider this curve and then just renormalizing it so that their overall kind of area or the amount of sands is equal to 1. Okay? So that is the conditional distribution defined over here. Yeah, over here. So back to this male or female example. Okay, so so this guy, the P of x, which is placed in the denominator. Okay, so that is obtained by first considering this joint probability, and then summing up all the possible values of this guy, right? And then, so here, this joint distribution or joint density is determined or represented in this form, right? And then here, up to this point, or previously, we defined this distribution. So this guy, where y is set as female, and then we define the distribution as this form, having the mean of 160 and having some variance. And then for the male case, and then this guy is our, this is basically called a likelihood function, right? And so this guy is, more exactly this guy. P of x when given y is being equal to 1, or this male case. Right, this male case. So this guy, but we didn't consider this P of y being equal to 0 or 1, right? So this is called a prior, right? And so in this case, y is 1 or 0, and then this is basically a Bernoulli distribution, and somehow let's consider or suppose or assume male is a little bit more than female in the world, and so suppose the probability of observing male is 40% and 60% and 40%, and suppose this is our initial or prior probability distribution. Okay, and then now we understand this part. And now it's time to plug this guy by incorporating this prior distribution, and then this guy is 0.4 and this guy is 0.6, right? Okay, then now let's think of this numerator. So again, overall story is we want to consider this posterior distribution of when given x as a fixed value of 168, and then what is the probability distribution of y, okay? And then this is corresponding to the reverse order of our generation process, and then we just changed it into this form, right? And then we just replace them just so that we can follow the natural generation order, which is like P of x comma y is given as this guy, P of y times P of x times x given y, and P of x, which is marginal distribution, is also represented as this natural generation order, and then considering all the possible cases of intermediate node of y. Okay. Okay, then in this case, x is again fixed as 168, and then it is of course the function of y, right? And then in order to obtain this function, let's consider y being 0 and x is equal to this, and y is equal to 1. Okay, so there is no other values. So if we can specify each of these values, and then it is the same as defining the full definition of this p of x given p of y given x, right? Okay, and then and then this guy is so this guy is represented as this, and then p of x is represented in this form, and then we consider this case of y being 0, right? And so give me 1 second. Okay, so here the numerator should also follow this y being equal to 0, right? And so in this case, p of y being equal to 0 n times p of x is equal to 168 given y is equal to 0. Okay. So p of y being equal to 0 is defined as 40%. So this is 0.4. Oh, yeah, sorry that it is quite messy, but again, the high-level story is that this posterior is defined as this prior times likelihood, which just follows the natural generation order, but we divide it by p of x because in this posterior we have x as our condition, right? And then x is fixed as 168, which is our particular feature vector or feature value, right? And then in order to compute this p of x, and then we considered all the possible y's that will generate the same 168, which is in this case these two cases, right? Whether y being 0 or y being 1, right? And then now in the case of numerator, in the numerator is naturally following our order, but we want to obtain the this function value of when y is equal to 0, and then it will just correspond to the case of generating x when y is set as 0. So we plug this y as 0, and then given y is 0, what is the probability of x? Okay. So that will correspond to like this. So suppose this guy, okay, this guy is maybe 2, and this guy is 0.6, for example, or let me use 0.7, okay, and then this numerator, okay, this numerator is, so this guy, when y is 0, and then we defined it as 40%, so 0.4, right, and then this guy, when y is given as a female, what's the probability of observing the feature value of 168? So that should come from this guy, red line, because that red line is p of the height distribution when the gender is fixed as a female. Okay, so that is corresponding to this guy. So the denominator, the numerator is 0.4 times 0.2. Okay, so 0.4 times 0.2 is this guy. And then that is actually corresponding to the first term when we perform the marginalization or computing p of an x by considering all the possible y's. So 0.4 times 0.2. And then what about the other case? So this guy is the gender being male, which corresponds to the probability of 60. And then this guy is when gender is fixed as male, and then what is the probability of observing 168, and that is corresponding to 0.7, right? Okay. So if you are familiar with the Bayes rule and their application to maximum likelihood, and also this posterior distribution, I mean computing the posterior distribution, and then it would be just a review of these contents. But if you're not, then I hope you guys have this clear picture from this simple example. Okay, so to summarize, P of y given x when x is fixed as 168, and then we first considered P of y given 0, which is female, and then it is like 0.4 times 0.2, right? And then 0.4, 0.2, and 0.6 times 0.7, right? So this is our P of x, right? X being equal to 168. What is the probability of observing 168 regardless of gender? And then simply we consider all the gender cases of being female or male, and then just the sum these joint probabilities all together, right? And then that will give us this marginal distribution, or the probability of observing this x being 168 regardless of any gender, right? And then the numerator is corresponding to just a specific or one case among all the possible cases. Okay. In this case, we obtained this, and if we obtain another possibility of being one or male, we need this guy. When still x is given as 168, and then in this case, we can see that. Okay. Let me just color code them in this one. So this is our posterior distribution of y. Okay, so y still have two possibilities of being female or male, right? And then this probability, suppose this probability, okay, so this is a 1.06, 0.16 and 0.84, right? So this is our posterior distribution of y when x is given as 168. And so in this case, what would be our classification rule, or what would be our optimal or reasonable rule? So we first considered this P of y given x, and then we considered all the possible y values being 0 or 1, and if it is a more than two classification problem, and then we will just compute this posterior probability where y is equal to 0, 1, 2, and so on, right? And then what will be our strategy or optimal policy? Our optimal policy is to just simply pick up the classification label that will have the maximum posterior probability when given this x is fixed as 168. Okay, so in this case we have 2. So simply by just comparing these two posterior probability, I mean the rule is quite obvious. So we will just pick up the class that is corresponding to the largest probability, right? Okay, so So if we know the full information of Px and P of x given, if we know the full information of P of y and also P of x given y, that follows this natural generation order. Okay, suppose we have the full information of these probability distributions involved in this generation process. Okay, and then we can just fully represent this guy. Okay, and then for each value of an x, we can just simply pick up the maximum possibility and its corresponding class label. Okay, so this is our quite obvious and quite reasonable classification strategy. So this is called Bayes classifier. Bayes classifier. Okay, so in this case, let me think of this process a little bit more by using this probability distribution. So we simply pick up the maximum value between all these possible cases, right? And then let me redraw. 접지가 뭐가 안 되나 봐. 저 HDMI는 접지의 중요성. 하여튼 네. Okay, so we considered the P of x, which is height, when y is given as a male or 1, or P of x when y is given as female or 0, right? And then in that case, this first distribution and the second distribution, the first distribution is something like this, and the second distribution is something like this, right? And then, we know, so from here, it was 168, 170, 160, and this guy was 0.7. I'm just redrawing the previous example, and this is 0.2, right? So in this case, we are not just comparing between these two, but also we just consider this prior distribution, right? So for example, we didn't just compare this 0.2 and 0.7 as it is, but we also considered this prior distribution, because the probability of observing male is a little bit higher than observing the female, right? So that is our prior. So intuitively from this graphical representation, we just multiply this male probability by 0.6, which is our prior distribution, right? So in that case, we just choose the 60% of the original height, and 60% of the original height, 60% of the original height, and then it will be something like this, right? So this is a 60% downscaled version of the original distribution, right? And then what about this guy? How much should we multiply this with? This is multiplying with the 0.4, because that is the corresponding prior, right? And so in this case, so we only choose only 40% of the original height, right? So in this case, something like this, okay? So overall, we originally represented this likelihood function, which is the conditional distribution of an x when y is fixed as a certain value. So y is fixed as a female or male, and then we consider these two separate distribution. and then we just downscale each of them by the corresponding the prior probability. Okay. Okay, and then from here, so this was originally 0.7, and then it was downscaled by the ratio 0.6. So this is our 0.42, right? And then from here, let's see. Okay, so this guy. So this guy coming from this left Gaussian or left distribution. Then that probability was 0.2 originally, and then we have to multiply this guy by 0.4, right? And so this downscale version, this guy is 0.08. Okay, so we compare these 2 points, which are coming from these differently downscaled likelihood function, right? And then what is our strategy of this Bayes classifier? It was just simple, just between the two, okay? So between this guy, and this guy, right? And then we just compare between them, right? And then just simply choose the maximum one. So that means given this fixed weight, and then considering their probability, considering their prior probability into the likelihood, so that we just properly downscale each of them, right, in their own manner, and then choose the biggest one or the largest value. So between these pink points, which one is larger? Of course, this one is larger, right? So what is the corresponding class for the y value? So that is definitely male. So this is the intuitive process of this Bayes classification or Bayes classifier. So in this case, so we can also consider another related notion called Bayes rule. Bayes rule, not Bayes rule, sorry. Bayes error rate. Okay, Bayes error rate. So Bayes error rate is, So we understand that this Bayes classifier is at least like impeccable or kind of perfect strategy that we can choose, because at a certain situation, we consider all the possible cases that we observe the same value coming from different label values, and then we simply choose the maximum probability of generating that particular value from a particular label value, okay, by just simply comparing between these two, right? So this is the Bayes classifier. But in this, even in this perfect kind of strategy, can we expect some error, or will it give us like 100% classification accuracy? So it is not, because in this case, we know that the same point of 168 actually can be generated both from male and the female, right? So here we basically assume, or we admit, that the same observation or same feature vector can have both of this label or that label. So it is just a matter of different amount of probability. Okay, in this case, can we say, in other words, can we say that the probability of observing this 168 from the females class, can we say that this probability is completely zero? It is of course not, right? Because even though the probability is small, but this 168 can still be obtained from this female root, right? So when the label is female, and then we can still obtain this, right? So in this case, if we just randomly generate our samples by just following this generation process, okay? So y is having the probability of 60 versus 40%, and then this likelihood is Gaussian, and the mean is 170, and maybe the variance or standard deviation is 10. And this guy is n 160, and maybe 10 squared, assuming that their variance is the same. Okay. So when generating our samples from all these perfectly known generation process, and then just assigning or just choosing this optimal kind of classification strategy called Bayes classifier, and then we can still obtain we cannot obtain the perfect or 100% accuracy in this scenario, right? Because the same value can be generated from multiple different labels, right? From this from our generation process. So in this case, we can consider the classification accuracy or error rate. Okay, so that error rate is called the Bayes error rate. So let's consider the Bayes error rate. Bayes error rate. So in this case, we understand that this guy is the joint distribution when y is fixed as a female, and this guy is our joint distribution when y is fixed as a male, right? So they are discounted version by their prior value, so these are joint density, right? And so here, what is our Bayes rule in this case? So Bayes rule is this guy. So in this case, 168. So after downscaling or discounting by their prior value, so which one was larger? This guy, right? So in this region, it is of course the case where we choose this male class. And then where these two lines are crossing with each other, like in this point, right? So in this point, so yeah, using that as our boundary, looking at the right side of this boundary, then we can see that this cyan-colored mountain is higher than this green line, right? So this is our Bayes rule. So if our feature value is found to be larger than this value, and then that's when we just classify it as male. And the left side, on the contrary, this green line becomes higher relatively compared to this cyan line. So this is when we just classify it into the female. Okay. So still in this case, we understand that error can still occur, and what is the error rate or the probability of errors? So that error is this guy. So what if our data was generated from this region? Okay, so that region is still, it's right side of our Bayes classification rule, or yeah, this larger than this threshold. Okay, this threshold is basically the Bayes decision boundary, right? But still, yeah, this amount, right? So this amount can still be generated from the female class, right? So this is an unfortunate case where we commit, or yeah, this misclassification happens, right? And then also this part. So this part is also another unfortunate cases, right, of performing or committing the misclassification. Okay? So summing these two up, And then these would, yeah, the summation of these two probabilities will be our classification error rate. Okay, so suppose the summation between the two is like 8% in total. 8% in total. So in this case, Bayes error rate is 8%, and this was achieved. This was achieved when, yeah, even when we know full information about y, I mean the probability density of y and x given y, right? So we didn't miss, or there were no missing information in this process, right? So in this case, even when we have the full information to model our posterior distribution of this guy, and then just simply choosing our classification strategy as this optimal one called the Bayes classification or Bayes classifier, and still from our data we have to admit that we will see 8% of a misclassification error, right? So yeah, hopefully this one, this kind of an this observation or phenomena can give you kind of intuition that, yes, suppose you you built your own model based on deep neural network, and then you perform some task, and it is for example a binary classification task, and then suppose your classification accuracy came out as maybe 87%, okay, 87%, and then you will do your own kind of hyperparameter tunings, and then supply more and more data, training data, and so on. And then somehow you obtained 89%, and so on, right? But still, even when you do anything that you can do, giving more and more data and using a more and more advanced networks, you cannot achieve more than 90%, 92% of an accuracy, because inherently 8% of this classification error, is the minimum possible one. Okay? Even when you have the full information of your data or the generation process. So in practice, our situation of modeling the new neural network or doing the hyperparameter tunings and so on, in this case, we don't even assume any kind of generation process or any of this, this kind of thing, x comma y, or x, p of x given y, and so on. So we don't even consider these. And that means we don't have the full information about these probability density that gives us kind of full information of our feature vector, and also the label values. But even though it is unknown, but there is some upper bound of your task, upper bound of your task that you can achieve, or you cannot overcome, or you cannot exceed, from your task. So that is coming from the inherent limitation that even the same feature vector can have like two possible or multiple different label values. Any questions so far? 네.
저 8%를 줄이기 위한 방법은 없는 건가요?
네. 이거는 그러니까 약간 이런 거예요. 그러니까 어떤 데이터를 예를 들면 누구는 이거를 뭐 감성 분석이다. 이걸 누구는 똑같은 문장을 이제 누구는 이거는 긍정이라고 얘기를 하고 누구는 부정이라고 얘기를 하고 약간 애매한 것들이 있잖아요. 걔네들을 애초에 맞게 클래스파이 한다는 것 자체가 조금 약간 말이 안 되는 케이스일 수 있고, 그 다음엔 거기서 나타나는 어떤 이러한 probability distribution이나 뭐 이런 어떤 두 개 간의 이제 비교를 한다는 거는 뭐냐면 이제 이게 약간 긍정이라고 했을 때, 긍정이라는 레이블이 주어졌을 때 그 긍정이라는 레이블 내에서 뭔가 신이 이제 긍정이라는 거를 이제 가정하고 거기서 이제 긍정에 해당할 법한 긍정의 감성 분석에 해당할 레이블에 해당할 법한 데이터를 막 만들어낼 때 그 중에 이제 그 문장을 이제 생성할 확률이 한 요 정도 되고, 부정이라고 했을 때 부정에 대해서 어떤 그 랭귀지 모델링이든 아니면 어떤 그 텍스트 혹은 센텐스가 막 제너레이션 될 때 우연찮게 똑같은 센텐스가 여기서 생성될 수도 있고 저기서 생성될 수도 있다. 이런 케이스가 만약에 우리 데이터 혹은 우리 태스크에서 존재할 수 있다고 가정을 한다면 이렇게 같은 어떤 그 샘플 혹은 같은 이제 피처 벡터가 같은 데이터 인스턴스임에도 불구하고 어떤 두 개의 레이블이 모두 다 가능한 케이스가 애초에 존재한다는 거예요. 그리고 그 중에는 애초에 존재한다? 그 말 이제 우리 클래시피케이션 스트래티지는 랜덤하게 한다. 뭐 이때는 내가 이때는 뭔가 약간 감이 약간 긍정인 것 같아서 딱 맞추고 저 때는 또 똑같은 문장이 들어왔는데 정보는 똑같은데 이때는 뭔가 내 이제 뭔가 5감 아니면 6감에 의해서 이게 내가 이렇게 운 좋게 맞출 수도 있겠죠. 그러면 예를 들면 뭐 이게 조금 이거보다 더 떨어질 수도 있지 않을까 싶을 수도 있지만 뭐 사실 그러기란 사실 쉽지 않고 그리고 우리의 이제 뉴럴넷이 뭐 여러 가지 내부적으로 뭐 VA나 뭐 이런 걸 써고 이제 랜더마이제이션의 요소가 만약에 없다면 기본적으로는 우리 뉴럴넷이든 뭐든지 간에 어떤 다 이거는 펑션이에요. 펑션이라는 말은 주어진 어떤 동일한 입력에 대해서는 무조건 동일한 아웃풋이 나와야 되는 이게 곧 펑션의 정의거든요. 그리고 우리가 펑션에서 이제 뭐 다들 알다시피 뭐 여기서 이렇게 화면 표했을 때 1, 2, 3, 4, 5, 6, 7 그러면 이제 펑션의 기본적인 데피니션이 뭐냐 이제 한 인풋에서 하나의 아웃풋을만 가야지 여기서 이제 뭐 이렇게 여러 개로 만다 이건 펑션 자체가 아예 안 되는 거죠. 네, 그래서 이제 우리 뭐 뉴럴넷 자체도 이제 코에피션트가 다 이제 컨버리가 됐다면 이거는 이제 이런 어떤 펑션으로서 역할, 즉 무슨 소리냐 주어진 입력 하나에 대해서는 어떤 정해진 아웃풋으로 가기 때문에 이 경우는 뭐냐면 이제 그 문장 하나가 주어졌을 때 그때 이제 둘 중에 항상 한쪽으로만 이제 답을 내준다는 뜻이 되고 이렇게 되면 둘 중에 이제 어느 게 더 많이 생성이 될 케이스냐 그럼 그쪽으로 해는 게 당연히 우리 클래시피케이션 액큐러시 치면은 더 좋고 그럼 이쪽은 어떻게 되느냐 버리는 거예요. 포기하는 거죠. 거의. 네.
그러면 지금 제너레이티브 모델에 관한 설명인 거잖아요.
네.
근데 제너레이티브 모델에서 분포를 정확하게 알 수 있다면 그러면 그러니까 저게 PXY에 대한 분포를 정확하게 알 수 있다면 우리는 확률을 정확하게 계산해낼 수 있다라고 말씀하시는 거죠?
네.
근데 그 경우에도 저런 에러는 무조건 발생할 수밖에 없으니까 그게 최소의 에러인 거죠.
네. 이거는 이제 뭐 죽었다 깨도 시간이 많이 잖아. 뭐 하여튼 뭘 해도 저 에러레이트보다 더 잘 나왔다니까 누군가 이래요. 뭐 챌린지 어떤 내가 문제를 이제 챌린지를 내가 만들었어요. 뭐 QA 챌린지든 뭐 시멘틱 세그멘테이션 하시고 OCR 막 챌린지 만들어갖고 내가 이런 뭔가 제너레이션 프로세스를 내가 완전 신이어갖고 완벽하게 알고 있고 그래서 이제 예를 들면 뭐 그때 나오는 에러레이트, 베이스 에러레이트를 딱 계산해줬어요. 근데 서브미션 중에 어떤 애가 갑자기 뭐 저거 92%보다 높은 게 서브미션이었다? 그건 뭔가 잘못된 거라는 거죠. 네, 근데 이제 현실은 저 베이스 에러레이트나 저거를 뭐 혹은 풀 제너레이션 프로세스에 대해서의 그 어떤 풀 인포메이션이 이게 기본적으로는 이제 없으니까 그러니까 저거를 계산할 수는 없지만 네, 기본적으로는 하여튼 뭐 예를 들면 뭐 성능을 뭐 이렇게 해도 죽어서 깨나와도 뭐 예를 들면 뭐 나는 한 95%를 내야 이제 나는 논문을 내고 싶은데 이 태스크가 아무리 해도 88%밖에 92%밖에 안 나온다 그러면 뭔가 더 해서 될 일이 있고 뭔가 더 해도 안 될 수 있다는 거예요. 물론 뭐 이렇게 해갖고 이제 뭐 뒷걸음치다 하나 얻어걸려갖고 어떻게 93% 나왔다. 근데 그게 사실 의미는 전혀 없는 거일 수 있다는 거죠. 근데 물론 저걸 몰라요. 우리는 베이스 에러레이트를 계산한다는 것 자체가 애초에 불가능하기 때문에 그걸 모르는 상태에서는 그 어퍼 바운드도 모르지만 기본적으로 해도 어퍼 바운드가 뭔가 있을 수는 있구나라고 우리가 알고 있는 것 자체와 그렇지 않은 거. 이건 내가 열심히만 하면 나는 100%에 갈 수 있겠지 언젠가 이렇게 생각하는 것과 애초에 이게 불가능하다라고 이제 인정하는 것과는 애초에 좀 뭔가 접근 방법이나 뭐 여러 가지가 좀 달라질 수 있다.
지금 소시에 모여서 그 디스크리미너티브 모델하고 제너러티브 모델이 두 가지가 있잖아요. 근데 그 겐에서 제너러티브 어드버서리 네트워크에서 제네레이터랑 디스크리미네이터가 있잖아요. 그 거기서 말하는 두 개가 같은 말인가요? 아니
다른 말. 네, 이거 한마디만 하고 쉬는 시간 가지면 이제 계속 얘기했던 제너러티브 혹은 디스크리미너티브 모델에서의 기본적인 차이는 뭐냐면 지금 여기 과정에서 기본적으로 우리가 사용한 요소들 어떤 정보들을 우리가 썼는지를 보면 일단은 prior distribution, 뭐 이거는 뭐 그렇다 쳐요. 뭐 이 레이블을 그냥 피처 밸류에 상관없이 이 레이블들을 관찰하는 어떤 비율이 대충 뭐 키는 보지도 않고 뭐 그냥 아무나 뭐 집히는 사람 이렇게 딱 했을 때 확인해봤더니 이게 남자다 여자다 이게 60% 40% 이거다라는 거거든요. 근데 이건 prior까지는 뭐 괜찮을 수 있는데 예를 들면 이게 각 그 prior의 값이 하나의 값으로 설정됐을 때 그때 나오는 어떤 likelihood, 그러니까 두 세컨드 스테이지에서의 요거에 대한 확률 디스트리뷰션이 이 노멀이라는 건 우리가 완벽하게 다 알고 있다는 뜻이잖아요. 이렇게 뭔가 완벽하게 알고 있다라고 접근을 하는 것 자체가 이게 이제 제너러티브 프로세스가 되고요. 그다음에 지금 보면 이렇게 쭉 이렇게 과정을 거치긴 했지만 결국은 이제 베이스 룰의 그러니까 베이스 클래시파이어에 기반해서 그 클래시피케이션 룰은 결국은 되게 심플해요. 여기서 나오는 이 바운더리 혹은 이 threshold보다 오른쪽으로 넘어가면 메일, 왼쪽으로 넘어가면 피메일 이런 거잖아요. 네. 그리고 이거는 또 어디서 나왔느냐? 바로 어디서 나왔느냐? 가만 생각해보면 여기서 나온 거잖아요. 이 posterior distribution 혹은 이 제너레이션 프로세스를 이제 역전을 해놓은 그러니까 거꾸로 뒤집어 놓은 x가 하여튼 주어졌을 때 y에 대한 디스트리뷰션이 어떤지. 근데 이제 요거를 구하기 위해서 우리는 베이지 룰, 뭐 베이지의 클래시피케이션, 뭐 베이지 클래시파이어, 그다음에 뭐 에러 레이트, 그다음에 베이지 룰이 나왔는데 일단 뭐 네, 요거를 이제 이렇게 나타내는 게 베이지 룰이죠. 요거를 요게 이제 베이지 룰이잖아요. 그래서 이거를 지금 써서 그래서 이거를 쓰고 나면 이제 이 조인트를 우리가 생성을 하는 그 내추럴한 오더인 이렇게 나타내고 그러면 요거 프라이어 집어넣을 수 있고 또 요거 우리가 아까 정의한 노멀 디스트리뷰션으로서 우리가 정의를 그냥 했잖아요. 그걸 여기다 싹 대입을 하면 되는 거죠. 이렇게 했을 때는 이제 우리가 그 제너레이션 프로세스에 대해서 이제 풀 인포메이션을 다 갖고 있다고 생각을 한 거예요. 그러니까 이게 어떤 정해진 y 값에 대해서의 x에 대한 디스트리뷰션 자체도 우리가 그 각각의 모든 y에 대해서 다 알고 있다. 그 과정이 여기 들어가는 거예요. 그래서 이게 제너러티브 모델이라고 해요. 그러니까 제너레이션 프로세스에 대해서 우리의 풀 인포메이션을 다 알고 있다라고 가정할 때. 근데 이제 디스크리미너티브 모델은 이제 뭐냐면 결국 우리가 필요한 건 우리가 베이지 클래시파이어에서 필요한 거는 뭐냐는 결국 이거잖아요. 이거 요 포스틸 그죠? P of y given x 그러면 우리는 이게 제너레이션이 y 그 다음엔 x 뭐 이렇게 뭐 됐겠지만 그거를 우리가 다 무시하고 그거를 뭔가 다 바이패스하고 우리는 딱 얘만 모델링을 하는데 집중을 하는 거예요. 집중을 한다는 게 제너레이션 자체에 대해서 이게 가우시안이었는지 뭐였는지 아무 상관 안 하고 우리는 딱 뭔가 얘만을 어떻게 바로 한 방에 좀 모델링을 하겠다라고 접근을 하게 되면 그러면 이제 이거를 디스크리미너티브 그런 방법론이라고 부르고요. 그러면 이 경우는 이제 아까 이야기했던 아까 우리가 사용했던 혹은 이 중간 과정에서 유도 과정에서 활용했던 이런 거 P of x given y equals 0 or 1 이거에 대한 디스트리뷰션이 하나도 없이 지금 우리는 이거에 결국은 x, y가 거꾸로 된 그 디스트리뷰션만 얻어내면 되는데 제너레이션 프로세스가 있던 이렇게 좀 뭔가 이런 이 순서를 따른다고 했으니까 그렇게 가정을 했기 때문에 그리고 그러다 보니까 이거 중간 단계에서 나타나는 얘에 대한 어떤 풀 인포메이션을 우리가 가정을 했을 때 그럴 때 그거를 사용을 해서 뭔가 이제 그 P of Y given X 이걸 뒤집은 것까지 오는 요 과정이 이제 제너러티브 프로세스, 그러니까 제너레이션 프로세스를 풀리 다 알고 있다라고 해서 이제 제너러티브 프로세스라고 하고 또 이제 그 아까 이런 과정 없이 바이패스하고 저거면 바로 구할 수가 있는 요걸 그러한 방식이 디스크리미너티브 방법이고 이제 또 다음 시간에 우리가 보게 될 이제 바로 이어서 보게 될 이제 로지스틱 리그레션 같은 경우 이 어프로치를 취하는 거예요. 그러니까 어떤 제너레이션 프로세스도 내부적으로 가정하지 않았는데 딱 요것만 이제 우리가 모델링해서 뭔가 얻어내는 그런 식이 이제 또 디스크리미너티브. 그래서 그래서 이제 또 배우겠지만 이제 프리뷰로서는 이제 로지스틱 리그레션과 지금 이렇게 제너레이션 프로세스 그리고 그 제너레이션에서의 이 라이클리후드 값, 요놈 y가 결정이 되고 나서 x에 대한 디스트리뷰션이 하필 또 가우시안이다라고 뭐 이게 가우시안이 아니라 유니폼도 될 수 있고 다양하게 될 수 있지만 하필 또 이걸 가우시안이라고 가정했을 때 우리가 이제 또 그때 이제 만들어지는 클래시피케이션 룰이나 그 클래시파이어가 이제 우리는 이제 리니어 디스크리미넌트 어널리시스라고 부르고요. 그래서 이제 로지스틱 리그레션은 디스크리미너티브한 어떤 대표적인 방법이자 리니어 리그레션은 이제 대표적인 제너러티브 방식이 되고요. 그래서 똑같은 일, 그러니까 결론적으로는 일로 가든 절로 가든 사실 그 클래시피케이션 룰은 뭐 지금 우리는 이제 심플한 어떤 스케일러, 그러니까 x가 스케일러라고 봤지만 이제 x가 피처 벡터, 우리가 멀티 디멘셔널인 경우도 당연히 또 따져줘야겠죠. 그 경우에는 이 경우 가우시안의 정의를 하고 그러면 이제 그게 어떤 가정, 그러니까 가우시안에서 여기 뭐 여기서 이제 가정한 요 베리언스가 이제 똑같다, 베리언스가 똑같다라고 가정을 하면 이게 그 여기서 나오는 베이즈 클래시피케이션 룰 아니면 이 베이즈의 디시전 바운더리가 반듯한 이제 피처 값들이 이제 리니어 컨비네이션 형태로 나타나거든요. 네, 그거는 로지스틱 리그레션이나 이 LDA나 다 똑같이 이런 리니어 클래시피케이션 바운더리를 주지만 저 이제 풀 제너레이션 프로세스를 가정을 했을 때는 그게 LDA에 해당이 되고 그거 없이 그냥 바로 포스티리어를 바로 이제 모델링을 하는 방식이 그게 이제 로지스틱 리그레션이라고 불리게 됩니다. 네, 요거. 네. 그래서 일단은 뭐 그러한 것들을 또 쉬는 시간을 좀 가지고 이거 또 10분 후에 5시 15분에 다시 시작할게요.
저희 그 신약개발 발표 자료요. 발표 시간이 혹시 어떻게 되나요?
다시 모르겠어요. 전혀 알려진 거 없고 이게 사실 아직 그 서면 평가라고 1차 평가가 있어요. 서류반으로 하는 거기서 지금 붙어야지 발표했다고 하긴 하는 건데 사실 어떻게 보면은 지금은 우리가 하고자 하는 그 연구 제안 내용 있잖아요. 그거를 조금 더 잘 설명해 줄 수 있는 슬라이드를 만든다, 조금 정리하는 형태로 만든다라고 생각하고 템플릿이나 아니면 분량 같은 건 생각하지 말고 뭐 연차별로 각 태스크 혹은 연구 내용별로 그것들을 좀 그것들 이제 이거 요약한 아니면 그걸 정리한 형태로 슬라이드를
그러면 저희 연구가 세부 3에 관련된 연구만
그렇죠.
되는 거죠? 다른 총괄 연구는
네,
되는 거죠?
맞아요. 그쪽에서도 알아서
교수님,
네.
아까 다운 스케일이 되셨는데 디스트리뷰션 다운 스케일은
다운 스케일 하는 이유는요. 이게 지금 보면 이게 아까 여기서 이제 0.2랑 0.7이라는 게 나왔을 때 이제 그냥 여기서 심플하게 0.7이 0.2보다도 높으니까 그냥 얘를 취하고요. 예를 들면 딱 여기에 해당하는 점, 딱 타이가 되는 거잖아요. 딱 똑같아지겠죠. 그러니까 여기는 반반이고 이쪽부터 넘어가면 뭐 그렇게 되고 이쪽으로 프리메일로 되고. 그러니까 이게 실제로는 이게 아니라 실제로 우리는 조금 설명이 좀 정할 수 있었는데 우리는 이제 지금 요거를 맞습니다. 이게 아니라 지금 요거를 따지는 게 아니라 즉 x 기분 y라는 probability density가 있을 때 여기서도 사실 x를 168로 고정을 시키고요. y가 0일 때와 1일 때 그때 각각 케이스에 대한 그 0으로 고정됐을 때 168에 대한 probability가 나오고 1일 때 그게 나오잖아요. 지금 이거를 가지고 이 argmax를 취한다는 것은 바로 지금 이 두 개의 그래프를 놓고 어떤 특정한 168일 때 누가 더 높은지를 보겠다는 건데 지금 여기서는 약간 다른 게 지금 우리는 이걸로 우리의 크라이테리아를 삼는 게 아니라 이거를 뒤집은 거. 그러니까 이거는 하여튼 y가 어떤 값이라고 할 때 x를 만들어낸 거잖아요. 근데 우리는 그 포스요, 즉 y가 그러니까 y 기분 x를 생각하는 거잖아요. 그럼 y 기분 x는 결국 이 라이클리후드에다가 아까 얘기했던 그 조인트를 이렇게 통해서 이게 모델링이 되다 보면 이제 이런 식의 이제 프라이어가 이렇게 붙는 거예요. 그러니까 지금 아까는 지금 얘랑 얘를 지금 비교를 하는 거였잖아요. 지금 요 시간, 그렇죠? 근데 지금 보면 이제 여기에 각각 이런 애들이 붙는 거잖아요. 그러니까 비교를 할 때 이 두 케이스 간에 이제 누가 더 높은지를 비교를 할 때 바로 이 프라이어가 고려가 된다는 것이고요. 그렇게 되면 그거는 결국 무슨 소리냐면 이 각각의 가우시안 이게 그러니까 y가 어떤 하나로 고정이 됐을 때 x에 대한 각각의 디스트리뷰션인 건 맞지만 여기다가 이제 그 y가 실제로 요 메일일 때와 피메일일 때 그때 이제 probability 프라이어인 60% 40% 요거를 고려를 해줘서 결국은 여기다가 이제 얘에 해당하는 프라이어 값으로 즉 얘는 40%였으니까 40% 낮추고 얘는 이제 60%로 낮추고 그 다음에 이 두 개 값을 비교를 한다는 뜻이 돼요. 네, 그래서 이제 여기서 직접 비교를 하는 게 아니라 아까 얘기했던 것처럼 그 두 개를 이렇게 그린 라인 이렇게 위로 갖고 왔을 때 그거를 60% 얘는 40%로 다운 시킨 후 그 다음에 거기서 나타나는 어떤 168이면 168이라는 요 고정된 값에 대해서 이 두 개 값을 비교를 한다는 거죠. 그러면 약간 이게 좀 이런 게 좀 있어요. 그러니까 이게 원래 이 두 개 라인을 그냥 고지고대로 비교했다면 그때 베이지 디시전 바운드는 여기가 돼요. 왜냐면 여기가 지금 역전이 일어나는 포인트거든요. 근데 이게 지금 보면 각각의 이 그 라인들이 그 디스카운트 되는 레이시오가 그 지금 아까 그 프라이어에 의해서 결정이 되니까 그 얘는 60%만 얘는 이제 40%만으로 확 더 많이 다운이 되니까 디시전 바운드리 측면에서는 더 이쪽으로 가서 키가 조금 더 작다 하더라도 이거는 이제 남자라고 클래시피케이션 하겠다는 거죠. 네. 네.
컨디셔널.
네, 라이브리후드가 되죠. 네.
근데 제 생각에는 그 이 확률이랑 이걸 더하면 1이 돼야 될 것 같은데.
아, 네. 어떤 거랑요?
예를 들면은 이렇게 설명해주잖아요.
네.
여자일 때
네.
188의 확률이랑
네.
남자일 때 68의 확률을 더하면은
네.
1이
아, 그렇죠. 이거 두 개는 이제 1이 되지는 않고요. 그러니까 정확하게는 지금 PO X 이삭의 이거에 Y가 0일 때 Y가 1일 때 이 두 개의 확률은요. 얘는 얘대로의 디스트리뷰션이 따로 있고 얘는 얘대로 디스트리뷰션이 따로 있기 때문에 이 두 개는 더해도 당연히 1이 안 나오죠. 그러니까 지금 여기서 만족하는 것은 이 그린 라인으로 솟아져 있는 이 두 개 있잖아요. 요거 하나하나의 그 산들이 썸투원이 되는 거는 맞아요. 네, 그렇지만 예를 들면 어떤 한 지점에서 이 두 개의 그 산의 봉우리를 값을 가져와서 이 둘은 합이 1이 안 되겠죠. 예를 들면 이런 데 갖고 왔어요. 그럼 이게 두 개의 합이 당연히 1이 안 되겠죠. 그러니까 이거는 지금 기본적으로는 두 개 서로 다른 디스트리뷰션으로 나왔다. 네, 포스티리어는 이제 합이 1이 돼요. 네, 포스티리어. 네. 네. 네.
질문만 들으셨어요.
아, 네. 네. 제네레티브 모델. 얘를 굳이 명시적으로 어떤 probability distribution이라고 정의하지 않는 게 걔는 존재는 해요. 그 probability distribution은 뭔가 있긴 있어요. 그렇지만 그거를 뭐 예를 들면 우리가 이거는 무조건 가우시안을 따른다. 그 가우시안에서 평균과 분산은 뭐 이런 거다. 뭐 이렇게 정의를 굳이 하려고 하지 않는 게 그게 이제 디스크리미너티브.
그럼 요거를 하면 사실상 요 분포를 어느 정도 추정을 할 수 있잖아요. 사실상 X를 어느 정도 제네레이션 할 수 있다는 거랑 같은 말이니까.
아, 네. Y가 고정이 됐을 때 X에 대한 X가 거기서부터 생성되는 제네레이션, probability distribution이 뭔가 그래도 우리가 명확하게 아는 디스트리뷰션 클래스로 정의가 된다. 근데 그거를 굳이 우리가 아는 어떤 걸로 정의를 하려고 굳이 하지 않는 게 디스크리미너티브. 네. 네. 아, 예, 안녕하세요, 교수님. 예. 아, 예. 제가 네, 죄송합니다. 제가 지금 오늘 하루 종일 수업 좀 있어갖고. 네. 네네. 지금 쉬는 시간, 네네. 예. 아, 3월 25일이요. 그때는 제가 저기 지금 오늘 저기 월요일에 저기 수업 6시 15분까지 있어가지고, 네네. 네네. 식사는 괜찮습니다. 예. 네. 예, 알죠. 예. 네이버 또 예전에 네이버 정보 갔을 때 이제 좀 이야기도 하고 뭐 그랬습니다. 네. 네네 좋죠. 네. 예, 알겠습니다. 네. 네. 그거 아주 좋죠. 네. 저희가 오히려 저희가 약간 좀 꼴린다고 해야 될까요? 네. 일단은 뭐 저도 뭐 자세하게 모르겠지만 일단은 뭐 좀 약간 국제적으로 좀 나름 알려져 있는 분이라. 네. 알겠습니다. 네. Right. Let's continue. Okay, so related to the question that I received during the break. Okay, so let's consider the Bayes rule in this case. So if we just consider the likelihood of like P of X given the female and male, okay? So if we do not consider this prior, then what will be our classification boundary? That classification boundary will be somewhere like this, right? Crossing this point, right? But if we consider our prior, then we downweight or downscale or discount each of these mountains with a different ratio, right? So for this, we downscale 60%, and this guy we downscaled it further into 40, only to 40%, right? And so that has the effect of downscaling this guy with a less prior probability, much more, right? So it will become like more inferior in this competition between the two, right? So in this case, the crossing point is now like this point. So it's like having the effect of moving our classification or decision boundary from here to here, right? So you can consider this situation intuitively as the case where, so having the same prior distribution. So if we assume that the equal probabilities assigned to each class, male and female, they have the equal probability in the beginning. Okay, and then in that case, this is our decision boundary. So if it is a 165, and then if it is greater than that, and then we classify it as male, or if it's less than that, and then classified into female. Okay, and then now due to our prior probability of like observing male much more frequently than the female, right? Represented as a 60 versus 40% probability, right? So in that case, it has the effect of our this of moving our decision boundary towards the left. So it means, we are like classifying more cases as male, right? So that is reflecting our prior knowledge or basically some prejudice. Okay, and then now let's look into some two-dimensional feature vector case. And then, the overall process will still be the same. So let's think of this a two-dimensional space. And then these are the specific data sample and their label value. So in this case, suppose we have two class labels, okay, and then maybe that has a 60% and a 40% of probability. And then now we have this complicated decision boundary. But let's just imagine that we have P of x, which is a two-dimensional one, given y being equal to 1, or y being equal to 0. Okay, so this blue one is 1 and the orange one is 0. Okay, and then we can kind of imagine like a complicated mountain which corresponds to P of x given y being equal to 1. Okay, so we can think of like a blue kind of mountain. And then also we can think of the likelihood of like x or P of x when given y is given as 0. Okay, so in that case, suppose we have some probability distribution corresponding to this blue mountain. Okay, and then given these two likelihood functions for each of y being equal to 1 or 0, right? And then we just downscale these two mountains with a different ratio of 60% and 40% respectively. Okay, and then for each value or each feature vector for each position, we just determine which mountain has higher is higher than the other mountain. Okay, and then we can think of that kind of decision boundary like this guy. So suppose this guy is our base classification boundary. Then it means that we can think of this underlying kind of mountain that is scaled down by their respective prior distribution, and then for each point, and then which one is a higher between the two mountains, and these boundaries are those crossing points where the two mountains' height is actually the same as each other. Okay, so in this case, we can actually see the actual misclassified one. So for example, so these regions are the orange and the blue regions, right? And then how about this guy, right? Or this blue guy. So they are clearly in the wrong side of this decision boundary, right? So these points were actually generated from this minor class, right? So these are, even though the mountain height is lower than the other mountain, at this particular point, at this particular position, we may have a larger mountain and a smaller mountain, and that guy came from the smaller mountain or the less probable class, right? So these points will give us the errors from this base classification rule or base classifier, and so we can actually simulate. I mean, if we assume that we have a full information of this generation process, or like this Bernoulli distribution with its own or specific parameter fully known, right? and then their complicated mountain is fully known, and then we can just simulate this data generation process. We just simply pick up or choose y value first with a certain prior distribution with the 60% and the 40%, for example, and then if it was sampled as a class 1, and then we have their own p of x given the class is 1, right? And then from there we can obtain these two-dimensional sample, and then still that label, the label of this data is the y value that this data is generated from. Okay, so in this case we can still obtain this value that is coming from this blue kind of label or blue class. Okay, so in this case, if we know this full generation process, and then we just obtain this random sample by following this two-step or this hierarchical generation process, and then we can also obtain this Bayes optimal classifier, and then still measure how many data samples are misclassified from this Bayes classification, Bayes classification rule, and that way we can kind of estimate. We can estimate the Bayes error rate, which is the upper bound or the best possible error rate, okay, from this simulation. So it can be viewed as kind of a Monte Carlo simulation. Any questions? 네.
앞선 페이지에서
네.
저 영역이 처음에 그 베이즈 클래시피케이션 바운더리가 포스테리어 디스트리뷰션으로 인해서 더 넓어졌다. 앞선 케이스에서
이거요? 이거요?
아니 그 베이즈 옵티멀 클래시피케이션.
투디멘셔널 케이스? 이거요?
저기서 처음에는 앞선 케이스에서는 프라이어가 0.4랑 0.6였잖아요.
네.
그거를 그대로 이제 바운더리를 표시하면 저 영역에서 0.6만큼 면적이랑 4만큼 면적인데 포스테리어를 구하면 그게 아까 같은 경우에는 0.84랑 그런 식으로 이렇게 넓어지는
이 에이리아의 레이시오가 뭐 처음에는 이제 라이트리후드를 혹은 두 번째 제너레이션 프로세스를 고려를 하지 않았을 때는 뭐 60대 40이었으면 뭐 6대 4로 뭐 약간 땅 따먹기를 뭐 이렇게 나눠 먹었다고 한다면, 라이트리후드를 고려를 했을 때 그게 이제 실제로 또 영역이 이제 몇 대 몇이 될지는, 몇 대 몇으로 이렇게 두 클래스로 분할이 될지는 굉장히 이제 좀 다양할 수 있어요. 그러니까 이제 완전히 익스트림한 케이스에서 보면 y가 이제 1일 때나 0일 때나 그때 이제 생성되는 likelihood 혹은 p of x given y, 그러니까 y가 1일 때나 0일 때나 그 conditional probability 이게 완전히 그냥 똑같아요. 완전히 똑같아요. 그러면 하나가 이 가우시안이고 또 이 가우시안. 그러면 이제 여기다 prior를 0.6, prior를 0.4를 곱하잖아요. 그리고 하나는 이제 0.6, 하나는 0.4로 이렇게 떨어지죠. 그럼 이건 모든 지역에서 우리는 얘 손을 들어줘야 된다. 어떤 지역이든 이제 얘 산이 더 높으니까. 네. 그래서 약간 이거는 좀 케이스 바이 케이스라고 볼 수 있어요. 또 다른 혹시 질문? Okay, so in the case of a k-nearest neighbor classifier, you know how it works. I mean, it's not directly related to our Bayes classifier. Okay, so it's just a particular classification algorithm. So in this case, if you watch it or studied CS231N or Stanford Convolutional Neural Net Deep Learning lecture, and then it discusses this KNN, K-nearest neighbor classifier in the first few chapters. and then it shows different examples when varying or changing this k values from 10 to or 3 or 1 and so on, right? And so if k is 1, and then the classification boundary gets more and more complicated, and then k is 100, and then this classification boundary gets becomes simpler. And so in this case, so in terms of a bias and variance perspective, so I'm not going to explain the details of these meaning of this bias and variance, but if k is smaller, and then bias gets higher and variance gets smaller, and if k is becomes bigger and bigger, and bias becomes higher and variance becomes lower, and here this guy, this purple dashed line is actually our Bayes classifier or Bayes decision boundary. Okay? So in this particular example, these are the simulated example. These are simulated examples are just based on a full information of a specific prior and likelihood or second step generation probability density function, and then we generated those sample data, and then we can just represent their optimal decision boundary from Bayes classifier. Then these are the k-nearest neighbor classifier learned from our sample by using k-nearest neighbor classifier, I mean their decision boundary and this guy. So this decision boundary becomes much simpler than the original or the true classification boundary. And in this case, compared to the true boundary, the classification boundary learned from k-nearest neighbor classifier becomes more complicated, right? So this is overly complicated, and so this, due to high variance of our model, low bias value, and so on. Okay, then so this is a simple graph that you already familiar with. So this is an iteration or maybe epoch. Okay, so if we proceed, or these number of epochs or iterations goes on, and then the training error is monotonically decreasing, right? And then these are the validation error, right? And then what is this dashed line? These are the Bayes error rate. Okay, so our validation error cannot be better than our Bayes error rate, because that is our upper bound of our error rate, right? So even though we don't know where this line exists, but we can kind of assume that such a line actually exists in our graph. Okay, then let's move to logistic regression. In the case of logistic regression, you guys know the logistic regression is handling or considering the binary classification case where the label is either 1 or 0, right? And then in terms of this Bernoulli distribution of our binary variable y, right? And then we just model this guy, the probability of this y or this class label being 1. Okay. Okay. And then this guy is defined as this, right? And then some of you may already know, but let me just briefly review how we can have an intuitive understanding about it. Okay, so suppose our height or input feature value is this guy, and then suppose we have this constant node as 1, right? And then we consider this a fully connected layer of AX plus B, right? And then between this and this guy, and yeah, we use it as a logic value. So this is one logic corresponding to the positive class or y being 1. And then yeah, suppose we have this virtual node that has always the fixed value of logic as 0. Okay, and then now we consider, I'm just drawing some computational graph of logistic regression. Okay, so in this case, it is now becoming e to the power of ax plus b, right? And then in this case, e to the power of 0, which is 1, right? And then now we just normalize them in a way that for e to the power of 0, and we consider this relative probability. Okay, and then in this case, this guy is, yeah, we just assume that this guy is P of y given x is equal to 1, and this guy is P of y given x, no. P is equal to 1 given x, and this guy P of y given is equal to 0 given a particular value x. Okay, so this is the assumption or the model that we just assume, okay, for our logistic regression. Okay, so in this case, once obtaining these two, and then we can still just apply the Bayes rule for this guy, right? So because we have only two classes, so we consider the probability of y being equal to 0 given a particular x value. So you can just think of it as 1/60 centimeter, and then whether it is a male or a female, or we just also think of consider the probability of 1 when given x is equal to 1/68. Okay, so we consider these two probabilities, and these two probabilities are just formulated as this guy and this guy, right? So why do we assign those two as these two respective posterior probability? It is not a matter of right or wrong type stuff. It is just a model assumption that we just adopt or we start with. Okay, so this is a logistic regressions assumption, and if you use some different binary classifier, then of course it will follow different assumption or different representation of this guy. Okay. And so here we know that this guy is like 51%, and this is a 49%, and then this is when we choose the positive class or class label being 1, and if it is a less than 50%, then that's when we choose the negative or y being 0, right? And still, from this perspective of Bayes classifier, it still follows this obvious but quite reasonable strategy, right? So when given x, we consider this posterior distribution or the distribution of y when x is fixed as 1/68, and then somehow we modeled this probability of y when given x is x being 1/68, and then from them we just pick up the class that has the maximum possible probability distribution, right? And then also if we just extend it to like softmax classifier, where we have more than 2 classes, and then instead of this dummy node, instead of using this dummy node, we assign a different node for each class, right, to produce its logit value, and then it has a ax plus b, and then also this guy will have its own linear combination representation of cx plus d, and this guy is ex plus f. So a, b, c, d, e, f are all independently obtained through our optimization process, but we do not talk about how to obtain their optimal value. I mean, we are just at this point we are just talking about their models and how we model these posterior probability in this model, right? And then we go through the same process of going through this exponential function, and then just once making them into the positive values, and then we compute their relative ratio, and then that will be assumed to be that will be used as our posterior distribution and their each probability, right? And then at the end, we will still apply this Bayes classification rule, right? Okay, so back to this binary case of a logistic regression. So in this process, okay, I just described the logistic regression case. So here, so let me ask whether we modeled this guy. Okay? What is the probability of an x when y being 0 or 1, right? We didn't model these two at all in this process, right? We just directly modeled this posterior, right? So in that sense, we call this as a discriminative model or discriminative classifier. Although we follow the specific procedure, but in this procedure, we didn't use any particular assumption about that second stage generation process and its full information about the particular distribution, right? We didn't need that in this overall process, right? So in that case, we call it as a discriminative model. Any questions so far? 더미 노드요? 이게 그러니까 이 익스포넨셜 이렇게 함수 전에 이렇게 넣는 걸 이걸 이제 우리가 로짓이라고 또 부르고요. 이 로짓은 기본적으로 이렇게 마이너스 무한대서부터 무한대까지 낼 수 있는 이런 어떤 선형 결합에서 뭐 마이너스 무한대부터 무한대까지 있는 값을 모두 다 이제 0보다 큰 값으로 몰아주는 거고, 그 다음에 하여튼 이게 기본적으로는 이게 직관적으로는 이제 로지스틱 리그레션이든 아니면 소프트맥스 클래스파이어든 뭔가 이제 익스포넨셜 펑션을 통해서 그 전에 나왔던 어떤 입력된 이게 양수도 될 수 있고 음수도 될 수 있는 이 값을 익스포넨셜 펑션을 통해서 뭔가 모두 다 양수로 만들어주고요. 모두 다 여기서 양수로 만들어주고 이 값을 각 클래스별로 이런 값들이 존재한다고 생각하고 이 클래스별로 나온 이 값에 대해서 상대적인 이제 비율로서 각 클래스가 나올 법한 그 포스티리어 프로바빌리티를 우리가 할당을 해주는 거거든요. 네, 그래서 이제 뭐 A가 이제 2x 플러스 3으로 이렇게 모델이 됐다. 근데 x로 입력으로 들어온 게 이제 마이너스 1이다. 그러면 이제 여기에 나오는 거는 1이 나오잖아요. 그럼 이제 EXP를 통과를 시키면 2는 얼마죠? 뭐 이렇게 하는 거 알죠? 여기 2. 네? 아, 네. 그렇죠. 2.718. 2.7 정도 되잖아요. 대충 2.7이라고 하고, 여기 별표에 해당하는 건 이제 2.7이고요. 2의 1승이니까. 그 다음에 이제 얘랑 대결을 할, 얘랑 이제 상대적인 이제 비율을 따지고자 하는 이 바이너리 클래시피케이션에서는 기본적으로 이제 우리의 가상의 적이라고 할까요? 아니면 네거티브 클래스에 할당이 되는 로직 값은 혹은 저희 익스포넨셜 펑션에 들어가는 입력 값은 무조건 0이라고 가정을 할 거예요. 그러면 이게 익스포넨셜을 통과시키면 이 별표 값에 나오는 값은 무조건 이제 1이 돼요. 결국은 여기서 나오는 값과 여기서 나오는 값과는 이제 두 개의 비율을 따져서 이제 이 어떤 y가 1일 때 probability distribution이 계산이 된다는 거고, 이제 2.7 플러스 1 하면 더하면 3.7이 나오고, 여기다 이제 2.7, 그러니까 뭐 대략 한 4분의 3 정도라고 생각해 보면 이게 대략 뭐 78%. 그러면 이게 여기 할당되는 값이 되고요. 이 두 개 중에 얘에 대한 비율은 당연히 22%가 되겠죠. 네, 이런 식으로 이제 posterior distribution을 모델링을 하는 거를 이제 로지스틱 리그레션에서 하는 거죠. 그다음에 이제 그 소프트맥스에서는 이제 더미한 어떤 버추얼한 네거티브 클래스를 로지스를 이제 0으로 고정시키는 게 아니에요. 이게 어쨌건 상대적인 거라서 두 개 간의 비교를 할 거면은 두 개가 같이 움직이거나 아니면 두 개가 같이 움직이는 상황을 그냥 일반성 잃지 않고 하나를 고정을 시키고 나머지 하나만 움직이는 상황으로 만들 수가 있기 때문에 로지스틱 리그레션은 이제 여기를 이제 0으로 고정시킨 셈이 되고, 이제 소프트맥스는 물론 소프트맥스에서도 마지막 하나, 그러니까 클래스가 예를 들면 5개가 있다 그러면 마지막 노드는 무조건 0으로 우리가 고정을 시켜도 괜찮지만 이렇게까지 굳이 안 하고 그냥 뭐 어차피 여러 개인 김에 그냥 다 리니어 그 커뮤니케이션 코에피션트를 다 할당을 해서 아까 ax 플러스 b, cx 플러스 d, ex 플러스 f라고 뭐 이렇게 각 클래스별로 3개의 클래스가 있다면 각각 다 이제 로직 값을 다 독립적으로 그들만의 선형결합으로 이제 그 각 클래스별 로직 값을 이렇게 뽑아줄 수 있고, 그거를 가지고 이제 또 역시 익스포넨셜 펑션을 통과시켜서 양수를 만들고 그 다음에 상대적인 비율을 따져서 이제 포스티리어 디스트리뷰션을 구하도록 하자라는 이러한 모델의 가정이 이제 그 소프트맥스 클래스파이어에서 일어나는 일이죠.
아까 테스트 데이터 에러는 전체 에러 레이트를 먼저 계산하잖아요.
테스트 데이터 에러는 네네네.
이게 테스트 데이터랑 트레이닝 데이터가 모두 다 잘 샘플링 되었다는 가정이 있는 거예요.
아 그렇죠. 그러니까 뭐 운이 좋으면 당연히 테스트 데이터에 대해서 뭐 조금 뭐 더 내려갈 수도 있고, 심지어 우리 테스트 그렇죠. 그러니까 저 베이스 에러 레이스는 기본적으로는 뭐 우리 밸리데이션 데이터 아니면 테스트 데이터가 100개밖에 없어요. 근데 그 100개가 예를 들면 다 그 베이지 룰에 딱 입각해서 아까 그 지금 이런 상황에서 이쪽에서는 이 노란색에서는 전혀 생성이 안 되는 거죠. 그렇게 운 좋게 우리 테스트 데이터나 밸리데이션 데이터가 그렇게 잘 나왔으면 그때는 사실 8%의 베이지 에러 레이시 있지만 그거보다 뭐 당연히 0% 에러를 만들 수 있어요. 그 100개의 데이터에 대해서. 그렇지만 이제 여기서 이제 아까 뭐 어퍼바운드라고 이야기하는 것은 이제 어떻게 보면 우리가 그 100개라는 한정된 데이터에 대해서 뭐 100%를 달성했다고 해서 그걸 그러면 우리는 100%의 정확도를 자랑하는 뭐 암진단 어떤 모델이다. 그걸 풀어보면 그 100개의 데이터만이 아니라 실제로 이 세상에 존재하는 수많은 데이터들에 대해서 테스트를 해보다 보면 거기서는 이제 다 약간 뽀록이 나는 거죠. 그리고 이제 8%라는 에러가 당연히 발생이 됩니다. 그런 개념을. Any other questions? Okay, so yeah, you now have a high-level overview of how to model this posterior probability from this logistic regression, right? And then now I'm going to describe a little bit different angle of understanding this logistic regression. So to that end, we define this odds. Okay? So this odds is defined as follows. So this is basically the ratio. I mean, we still consider only the binary classification case. Okay, we only have the two class and some positive class and the negative class for they will be 1 or 0. And also we know that this is following the Bernoulli distribution, where if this guy is, for example, 0.92, and then this guy is what? Is 0.08, right? So in this case, we can compute this ratio between the two. right? And then this is called art. Okay, this is called art. This is just the definition of this term art. Okay. So yeah, it is a little bit of a off topic, but yeah, I personally like gambling, and I enjoy the poker, and when I was in the U.S. and there is a dedicated channel that just shows the poker game in the U.S. Okay? And then suppose there is only two players are surviving in a single poker game, okay? And then suppose the opponent and I are just competing with each other, okay, using a poker game. And then at a certain point, when I have maybe two cards and following the Texas Hold'em rule, and then we have some card in an open, and then another two open card, and then another hidden card, and so on. And then at some point, when we only have like 4 cards, I forgot all the terms, but in the floor there are only like 4 cards at this point, and then it will automatically compute or internally compute all the probability of me kind of winning. Okay, so my winning probability is 92%, and then accordingly the other guy will have the winning probability of only 8%. Okay, so in this case, I mean, in this case still I will have more probability to win in this case. But what about this 0.6 or 0.4? So I still have larger probability of winning, right? But still, it's a certainly different situation to this, right? So in this case, somehow I can do all in, right? But in this case, it is quite risky to do all in, right? So in this case, from my own perspective as one player, okay, I can think of the notion of, okay, so what is the ratio of the probability of winning with respect to the other guy? Okay, so in this case, so let's just the ratio is 11.5, for example, right? So in this case, this number is interpreted from my own perspective that, okay, I have 11.5 times more probability of winning than the other guy, right? So this is the interpretation of an art. But in this case, it is like only like 1.5 more probability, or 1.5 times the more winning probability than the other. So it is not that high, right? So this art is used in this form. So in this, if this art is higher and higher, and then it's time to do more kind of aggressive betting, okay? Or you just reserve it, your card, or do some small bettings, and then look for larger winning from other guy. Because if the other guy is just a fold, they just fold at an early stage, and then I cannot maximize my winning money. Anyways, it's all about those strategy in the poker game, but you can think of this kind of odd in this manner, okay? And then also in this case, this odd can also be defined from multi-class cases, although it is, I'm not sure if that is formally defined mathematically, but in the case of a poker game, suppose the 3 players are playing, and then one of them is myself, and then, okay, so considering the first opponent, what is my odds of winning? Okay, so I have at least like 10 times larger probability of winning than that guy, and then I can do anything against that guy, but against this guy, my odds is a little bit lower than that. Okay, so in this case, suppose our probability, my probability of winning is 80%, and this guy is only 8% and 12%. In this case, my odd with respect to that guy is 10, but in this case, we can also compute the odd with respect to that guy, which is less than 10, right? Okay, So back to this binary case, this odd, or this odd ratio. What is the range of this value? So this range is the minimum value of this odd or smallest odd value is, of course, 0, right? So what if I have 0 probability and 100% probability of winning for the other guy? Okay? In this case, the minimum value is 0, but the what about the maximum value? So the maximum value is basically infinity, because if my probability is 99.9999 and so on, and then 0.01, right? In this case, I can increase my odd ratio infinity, to infinity. Okay, so in the case of logistic regression, this model is actually this odd, and more exactly, this guy is also having the conditional probability. These are all conditional probability where the condition is x, which is given as a particular value of our feature vector or feature value. Okay, so these are all posterior probability. Okay, so this odd is modeled as so I forgot the model class of this particular case, but in this case we modeled our odd ratio as exponential, e to the power of our linear combination. Okay, so our feature, we have our own feature vector. Then we form the linear combination of it using some coefficient to train or optimize, and then go through exponential function. Okay, so we model this representation as the same as this odd ratio between the two classes. So this is the assumption of logistic regression. Okay, and then if we rewrite it in this form, and then this is the expression that we saw in the previous slide, right? And then if we just take the log of it on the both sides of this equation, and then log of odds, which is called log odds. Okay, log odds is represented as our linear combination. Okay, linear combination representation. So in the logistic regression, we model the linear combination for this log odds between the positive and the negative class. Okay, and this log odds is called logit. Okay, and then this is exactly the same as this entire process. Okay, so it's just a different perspective of understanding the initial assumption or initial model setting of this logistic regression. Okay, and then now it's time to set up or determine our objective criteria given a training data to optimize or determine beta 0 or beta 1 in this particular case. So we can think of it as a linear regression because we have a linear representation with respect to our feature vector or feature value, and then how about this guy, log odds? Can we, if we can represent it as a particular value from our label, and then suppose when x is a 168 centimeter, then suppose this log odds is represented as 83, and if it is a 173, then the log odds is obtained as maybe 15, and maybe if it is a 166, then log odds is obtained as -4. It's just an example. So we have this linear combination representation, and then if we can obtain somehow the target value corresponding to this guy as this form, and then we can just simply perform the linear regression based on least squares or gradient descent, right? So if we take that approach, or if we follow that approach, then it is just simply like, beta 0 plus beta 1x, or this guy is 168 minus 3 squared, and beta 0 plus beta 1 times 173 negative minus 15 squared. So this is a squared loss that we use in general in the linear regression, right? So we formulate it as a squared loss, right, which considers the difference between the model output and the target value, and then just take the difference and then take the square of it and then sum them up over all the data items, and then we minimize it by just computing the gradient with respect to beta 0 or beta 1, and then we can obtain this beta 0 and beta 1 as our optimal value. But this is not the way we that's not the way we optimize our logistic regression for these parameters. Okay, so we don't do that. Okay, and that's because we cannot obtain the particular log odd value corresponding to each case. So we only know for this guy, okay, 168. Suppose our training data, and this guy was actually male, and this guy was actually male, and this guy was female. We only know about their specific label, but we do not know about, So in this log odd, if we know this P of X, so, and then we have no problem of obtaining this log odd. But in this case, we don't know P of an X. In other words, suppose X is a 173 centimeter, and then what is the probability of this guy being male, okay, given this X is equal to 170, right? We don't know the specific probability, but instead we only know, okay, this guy is male, okay, and the other guy or other example is female, and so on. So at a specific feature value, we do not know the actual probability value that can range between 0 to 1, right? So we only know their specific label, whether it is a 1 or 0, right? So to handle this practical kind of situation or issues, so instead of using this regression-based least squares loss or squared loss, okay, we actually utilize the maximum likelihood method. So what it means is, so from this equation, okay, suppose our feature vector was obtained as 173, and then we know its label is 1, okay, but this is a specific example, okay, but we do not know the corresponding probability of y being equal to 1 when given x is 173. So we do not know about it, right? But in this case, if this data sample had label of 1, okay, and then what is the corresponding probability? I mean, suppose this probability is is defined separately, and then what is the probability of observing the male given this 178 as a feature value? So suppose this guy is independently defined, okay, so that is defined as maybe 70%, and accordingly, because this is Bernoulli, so this probability is 30%, right? And then what will be the probability of observing 173, and 1. Okay, so in this case, yeah, if these are the true value, and then of course, observing that that male, given the person of being 173 tall, okay, in this case, observe the probability of observing that male person from this height will be 70%, right? Okay, so we do not know this probability, and this probability is represented as this guy, right? So, and this guy is the same thing, so they are just differently written equation from the same equation, right? Okay, so this is our model for representing the probability of the male class when x is given as some value, right? And then the probability is computed in this form. And then this 70% is the same as this guy, right? So if this guy is male, okay, then we maximize this probability. Okay, so suppose the current parameter values, and this guy is only 65%. Okay, this when x is 173, and then observing this actual data item that we collected as 173 and 1. Okay, in this case, given 173, and then our current model is saying that we have the probability of observing the male as 65%. Okay, but if our model is really reflecting our data, and then our data that we collected as our observation, okay, will have relatively high probability if the model is actually if model fits our data very well. Okay, so in general, we consider if this probability gets higher and higher, okay, and then the corresponding beta 0 and beta 1 and its corresponding model is actually better explaining our data. So that way we maximize this probability, which is, for example, currently 65% from maybe some random initialization, or in the middle of our training process, it's only generating 65% corresponding to this observing this data item, and then we will try to maximize this probability close to 1. Okay, and then suppose this another case of 163, and then it is labeled as 0, and then in this case, what is the probability of observing the female? Okay, in this case, this is corresponding to the male class, the probability of male class, and then 1 minus something. Okay, so this is corresponding to the probability of observing the negative class, right? And so when x is plugged, we plug in x as 163 into this representation, and then 1 minus this probability corresponding to y being equal to 0. Okay, that probability should be also maximized, right? So overall, in other words, if we observe this guy, and then we actually observed it as a male, and then we compute the probability of observing male from this representation, and then we maximize it. And if this another example, and then this guy is shown as a female in our observation or our training data, and then we obtain the probability of the female class by just using this equation, expression 1 minus this guy, and that should be also maximized. So that is the main idea of this maximum likelihood estimation. Because we are maximizing the likelihood or the probability of observing our fixed set of training data from some model. Okay, so we adjust our model so that the probability of observing our specific set of training data to be maximized. So maximum likelihood estimation can be represented in this form. So yeah, roughly following this kind of procedure, we can just separate, we can split our training data into one set having a positive label and another set having a negative label. And for the positive set, what is the corresponding probability of observing positive set? So that is this guy. Okay, this is just this guy, right? And then suppose we have a 30 example corresponding to male class. Okay, and then we will have 30 different x values: 178, 173, 169, and 187, and so on, right? And then this is the corresponding probability of being male. Okay, and then we just multiply all of them. Okay, because it is based on like observing some joint event. Okay. Okay, I'm gonna skip this part of explaining why we use this product instead of sum. But anyways, so we formulate this as the probability of observing all the positive class of our observations, and 1 minus this guy corresponding to the probability of observing negative class. And then, yeah, suppose we have 100 training data, and then 30 of them as positive classes, and then 70 of them is negative classes. And then for 70 of them, we apply this guy, and then altogether we multiply all of them to form the entire joint probability of observing each of our training data. Okay, and then we maximize this likelihood. Okay, and then typically or in practice, we just use this log of likelihood, right? And then this summation will become, this product for multiplication is changed into the summation, right? So we maximize this log likelihood estimation. Okay, then, so in the case of neural nets, we generally consider loss function. Okay, loss function. Loss means, so first of all, I want to emphasize that, in general, this loss function or loss value is always greater than or equal to 0. So we do not consider any cases where we have negative loss value. Okay, so again, loss function value is always positive or 0, right? And also, this guy is a measure we want to minimize, right? So the loss function or L of our training data and our model parameters, then we want to minimize it with respect to our entire set of parameters, right? Okay, and then so here in the case of logistic regression, in this slide we consider this a maximum likelihood, right? So we understand this as our likelihood that we want to maximize, right? And then in order to represent it or consider it as a loss function, we just change it into simply something different that we have to minimize. Okay, so this guy is something that we have to maximize, and then how can we consider the loss out of it? And then that is by just simply negating this guy as this one. So minus or negative likelihood. If that is minimized, then in this case, this guy is minimized. So we first apply, typically we first apply this log, and then negative value. Okay, so that way we consider negative log likelihood. Okay, so that is a quite widely used loss function for this logistic regression and softmax classifier. So in the case of positive example, so suppose x was 178, and then it happened. Yeah, it turned out. Yeah, it had a positive class, and then 178, right? 8 times 178, 178. So this is the probability of the class being 1, right? And then we apply log over here, and then put a negative sign over here, and then we minimize it, right? So this is the negative log likelihood that is used for logistic regression in binary classification case in many of the neural nets or any deep learning libraries. Yeah. Any questions so far? Okay, then okay, so back to this logistic regression case. Yeah, let's derive the Bayes classification rule in this case. So we know those two probabilities are given in this form, corresponding to positive and negative class, right? And so we perform arguments between them, right? And then, yeah, similar to like similar to this case. So altogether, once we obtain this prior and likelihood and so on, and then yeah, it is just boiling down to just comparing between these two numbers, right? These two numbers, right? And so similarly to in this case, so this is the two posterior probabilities. So which one is larger than the other? Okay, so that Bayes classification rule is just based on that is performed based on simply this guy, ax plus b is greater than or equal to 0 or not, right? So in that case, yeah, if it is a 0.1, okay, and in this case, it will be slightly greater than like 1, so 1.03, for example, and in this case, 1, right? So in this case, this is when the first guy is winning, right? And so our classification rule of Bayes classifier is represented as this one, ax plus b, this one, right? In this case, x is something like this, right? And then now let's think of our two-dimensional case of our feature vector. So in this case, it is still the same of checking whether this linear combination is greater than or equal, greater than or less than 0, right? So that way, even though we went through kind of complicated process of this guy, computing the logic and going through exponential function and so on, but at the end, or once we trained or obtained the all convergent or optimal parameters of an A and B, and then the classification rule is simply, the Bayes rule, Bayes classification rule is simply represented in this form, right? Okay, so the time's up, so yeah, I haven't discussed about this LDA, but we'll continue it next Monday. Okay, thanks. 잠깐만, 급한 전화가 와갖고. 예, 여보세요? 네네, 안녕하세요. 예. 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 아, 어떤 거요? 아, 그래요? 아, 네네. 예. 아, 네. 네네. 아이고, 네. 아, 네. 여기서 보자. 그거. 네네. 아, 네. 아, 그 원단이 밑으로 가나요? 그게? 예. 네네. 네. 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 네네네. 네. 예. 이게 그럼 언제까지 좀 해드려야 될까요? 제가 오늘 밤이라도 오늘 12시요? 네. 그럼 이거 저기 그 공문이 제가 지금 공문이 지금 제가 미쳐져고 그거를 체크를 못해서 공문을 지금 오늘 12시 내로 그걸 받을 수 있을지가 제가 조금 확실하지가 않은데요. 예. 그거를 제가 좀 지금 바로 좀 수정을 좀 해갖고 좀 다시 좀 연락을 드릴 수 있을까요?